When you hear the words Ice Age, you probably picture the Pleistocene, right? Woolly mammoths trudging through the snow, saber-toothed tigers, endless frozen wastelands. Well, I've got a bit of a mind-bending reality check to kick off this explainer. You are actually living in an ice age right now. Literally today, as you're listening to this, we are currently sitting right inside a massive, millions of years long planetary deep freeze. Okay, let's dive right in and shatter some major misconceptions by redefining what an ice age actually is. It's not just one continuous, never-ending blizzard. It's actually a vast period of time marked by a long-term drop in Earth's temperature, which results in permanent continental and polar ice sheets. But within that massive time frame, the climate pulses. It fluctuates back and forth between deeply cold periods called glacials, where the ice aggressively advances, and relatively warmer periods called interglacials, where the ice retreats. So right now we're enjoying an interglacial period known as the Holocene. The ice has retreated back to the poles, but make no mistake, the broader ice age itself, it is very much ongoing. To wrap our heads around how we're currently sitting in this planetary deep freeze, here's our roadmap for today. We'll define what an ice age is, look at Earth's 5 major freezes, uncover the mechanics of cooling, see how all this ice sculpted our modern world, and finally, we'll explore the future of ice ages. All right, Section 1. What is an ice age? Let's discover the deep freeze. It's honestly fascinating how scientists first unraveled this mystery. Picture this. It's the 1700s and early 1800s, and people are finding these massive, completely out-of-place boulders, called erratics, just sitting in the middle of random fields across Europe. Most geologists at the time were like, oh, vast floods must have washed them there. But locals, including a Swiss chamois hunter named Jean-Pierre Paradin in 1815, pointed at the deep scratches in the bedrock and said, no way. The glaciers used to be much bigger, and the ice literally pushed these rocks here. At first, the scientific elite called this totally absurd, but the evidence was undeniable. By 1824, scientists like Jens Esmark were proposing worldwide glaciations, and in 1837, Carl Friedrich Schimper officially coined the term Eiszeit or Ice Age. It was this huge light bulb moment where the scientific community finally realized Earth's climate history was incredibly dynamic. Moving right along to Section 2, Earth's 5 major freezes. We are zooming out to a cosmic timescale here. So here is the deal. Earth basically flips back and forth between 2 distinct states, greenhouse Earth and icehouse Earth. For the vast, vast majority of our planet's history, it's actually been in a greenhouse state. That means little to absolutely no permanent ice anywhere on the globe. We're talking tropical temperatures that could sometimes even reach the poles. But periodically, the planet shifts into an icehouse state, where permanent continental and polar ice sheets form. And our current reality, as I mentioned earlier, is an ongoing icehouse period called the Late Cenozoic Ice Age. This whole era actually kicked off about 34 million years ago when the Antarctic ice sheet first began to form. Now, looking across billions of years of history, we see 5 major freezes that have dramatically punctuated Earth's timeline. First up, the Huronian, over 2 billion years ago. This was likely triggered when the atmosphere was suddenly flooded with oxygen, which wiped out all that warming methane gas. Then there's the Cryogenian, a freeze so severe scientists literally call it Snowball Earth, where ice sheets may have reached all the way to the equator. Wild, right? Later we had the Andean-Saharan, and then the Late Paleozoic, which was actually driven by the evolution of land plants absorbing massive amounts of CO2. And finally, the Quaternary Ice Age, which began about 2.58 million years ago with the freezing of the Arctic. This is the exact one we are living inside of today. Which brings us to Section 3, the mechanics of cooling. Let's take a look at the planetary thermostat. So, you gotta wonder, what exactly turns Earth's thermostat down to a planetary deep freeze? Well, it's never just one thing. It's a highly complex, interlocking, perfect storm of cosmic and terrestrial mechanics.
Think of it like giant planetary gears working together to drop the global temperature. First, atmospheric composition is absolutely huge. If greenhouse gases like CO2 and methane drop, Earth loses its thermal blanket. Second, plate tectonics. When continents shift around and block warm equatorial water from reaching the poles, ice naturally begins to form. Ocean currents play an equally critical role. For example, the closing of the Isthmus of Panama about 3 million years ago completely cut off a vital warm water exchange between the Atlantic and Pacific, heavily contributing to our current glaciations. And finally, tectonic uplifts. When massive features like the Himalayas and the Tibetan Plateau rise up, they expose vast amounts of fresh rock. As this rock chemically weathers, it acts like an immense planetary scrubber that actually pulls CO2 directly out of the atmosphere.
And all of this builds into a very predictable cosmic rhythm. Over the last 800,000 years, the dominant heartbeat of this freeze and thaw cycle, the oscillation between advancing and retreating ice, has been exactly 100,000 years. This rhythm is driven by what we call Milankovitch cycles. Basically, these are predictable periodic changes in the shape of Earth's orbit around the Sun, the tilt of its axis, and its orbital wobble. When all these cosmic cycles align just right, they reduce the amount of summer sunlight hitting the northern hemisphere. That allows winter snow to survive year-round, layer up, and slowly build into miles-thick ice sheets. But there are incredibly complex system dynamics at play here too. Think of them as nature's gas pedal and brakes. Positive feedback loops accelerate the freezing. For instance, as ice grows, it increases Earth's albedo, which is basically its reflectivity. More white ice means more sunlight bounces right back into space, so the Earth gets even colder, which makes even more ice. Also, glaciers grind rocks into dust, which blows into the ocean, fertilizing algae that suck up more CO2. But thankfully, negative feedback loops eventually pump the brakes to stop a runaway freeze. As the world gets locked in ice, the atmosphere becomes incredibly arid and dry. Without moisture, you don't get the snow needed to maintain those glaciers. On top of that, the immense weight of the ice literally grinds the land down to sea level, exposing more dark ocean water. That water absorbs heat and eventually helps melt the ice back down. It's a beautifully balanced system. All right, moving to Section 4, sculpting our modern world. Let's look at the tangible scars left behind. Far from just being a period of really cold weather, these advancing miles-thick ice sheets functioned as unimaginable planetary bulldozers. I mean, during the last glacial maximum, so much of the Earth's water was locked up in ice that global sea levels dropped by an astonishing 110 meters. That exposed massive land bridges, allowing early humans and animals to migrate across continents. As the ice relentlessly scraped across North America, it literally gouged out the basins for the Great Lakes and the Finger Lakes, which eventually filled with meltwater as the ice retreated. It completely rerouted massive river systems like the Ohio River. Across the globe, it carved the deep, dramatic fjords of Scandinavia. And when the ice finally stopped advancing, it essentially dumped mountains of rubble and debris, forming entire landmasses like Long Island and Nantucket. It's truly fascinating to realize that our modern geography is literally defined by the melting scars of the last glacial maximum. To put that into perspective, if you visit Clark Reservation State Park in New York today, you can stand at the edge of a colossal, dramatic waterfall plunging into a massive gorge. The only thing is, it is completely bone dry. It's a ghost river. It was carved by unimaginable torrents of glacial meltwater thousands of years ago, before the ice retreated further and the water just found a new path. The scars of the Ice Age are absolutely everywhere if you know where to look. And finally, Section 5, the future of ice ages, a disrupted cycle. So, here is the million-dollar question. Based on that 100,000-year cycle we talked about, when is the next ice age actually scheduled to hit? Well, based on historical orbital data and the Milankovitch cycles, the current interglacial period we're enjoying was supposed to come to an end relatively soon. The next planetary deep freeze was originally scheduled to begin in about 1,500 to 11,000 years. But wait for it. The data shows that human-induced carbon emissions have pushed atmospheric CO2 so incredibly high that the next glaciation has likely been deferred by at least 50,000 to 100,000 years. And here's the kicker. Even if we somehow stopped all emissions today, the carbon already up in the atmosphere takes tens of thousands of years to naturally scrub out. The numbers plainly indicate that human activity has become a geological force powerful enough to break a 100,000-year planetary rhythm. The subtle nudges of Earth's orbital variations, those natural Milankovitch cycles that have reliably triggered ice ages for the last million years, are now being completely overpowered by anthropogenic forcing. The sheer volume of greenhouse gases we've introduced acts as a thermal blanket so thick that the slight cooling from our planetary orbit simply cannot trigger the required glacial accumulation. It's a staggering reality to leave you with as we wrap up this explainer. The next great ice age, a relentless cosmic clockwork that has sculpted our continents and driven human evolution itself, is on hold indefinitely, entirely because of us. So I have to ask, are we witnessing the permanent cancellation of Earth's natural planetary pulse? It is a profound thought to ponder the next time you look at a glacier, or even just a strangely placed boulder sitting in a field. Thanks so much for exploring this with me today. And as always, keep questioning the world around you.